Okay, so we're on this very important journey. Everything we've been doing up till now is all playing a role in this quest. You know how fast the quantity's value is changing at every moment. You want to know how much of it you have. So that begins with an exact rate of change function. Why? We know how fast the quantity's value is changing at every moment. We know that. That's exactly what an exact rate of change function tells us. We want to know how much of the quantity we have. So using that exact rate function, which I'm showing here is that red curve, right? Which is what? That's a set of points that were generated as two quantities changed, right? This is the rate of change function. Okay, and so what are we after? So we're working through this process to figure out how much do we have, like net accumulation or total accumulation, right? Those are very similar to each other. So any accumulation function we're trying to get out of this rate function. Okay, and where does that start? That starts with, so given that changing rate function, what do we do from there to make a step towards figuring out what the accumulation is? It's the first thing that we do. I know Aiden knows. I know Kyle knows, yes? Approximate rate of change function. What does that look like? What does that look like?
Straight lines.
Right, yeah. So the key is we're going to make an approximate rate function. And why are we making the rate function worse, right? So that makes it worse. We had this beautiful, perfect, exact rate function, and we make an estimate out of it. We make it inaccurate. Why do we do that? Yeah. Right, so that gives us constant rates, right? We make that approximate rate function out of constant rates. And with constant rates, now we can start generating changes, right? Changes in our quantity and then build up those changes. And then now we're talking about accumulation, right? Why? Because dy equals mdx. If we've got a constant rate of change, we can calculate a dy. Well, now that's a little change in our quantity. And that's accumulation. And then we can add up those dy's. And now we keep track and we're building a function, right? We keep track and build a function. Okay, so let's recap from last time. To get how much we had at x equals 6.75, for example, we've got the change from completed intervals. M dx plus m change in x plus m change in x from the completed intervals. And then we have a little bit more from the current interval. A little bit more change from the current interval. Again, it's just m dx again. So this function that we're creating, this one rule, right? We're trying to get an accumulation function in one rule. It really boils down to this. Adding up little changes in y. And each of those little changes in y is calculated by? How do we calculate each little change in y? M times the change in x. That's all it boils down to. Now, there gets to be a lot of details, but we got to keep that as the big picture. You're just summing up changes in y. M dx plus m dx plus m dx plus another little m dx. Okay, so last time we worked on the change from the completed intervals, and we said that we needed each individual rate. So what's the rate in the first interval? So to get this rate right here, I'm going to take r of what? R of a, right? R of a. A is that x value where we start accumulating. So there it is, r of a. So then the second interval, we need this rate of change, which we get from the left side. So it's going to be r of a, and we're going to go across one. Listen, we go across one complete interval to get to the start of the second interval, right? We go across one complete interval to get to the start of the second. So that's a plus delta x. And then how far do we go to get to the beginning of the third interval? A plus? We go across two complete intervals to get to the start of the third interval. That's where we're going to get our rate from the third interval. And then we have the change from the current interval. How far do we go? Across how many intervals do we go? That time will be 3. All right, so we saw that. So for the jth interval, how many intervals do we go across to get to the start of the jth interval? J minus 1, right? In every case. So in the third interval, we go across, to get to the left side of the third interval, we go across 2 intervals. To get to the left side of the second interval, we go across 1. So it's always 1 less, right? So if we're in the jth interval, we're going to go across. We're going to start at A, and we're always going to add. We're going to go across J minus 1 intervals to get to the left side of the jth interval. And so that's where we came up with this general form for what the x value for each rate is going to be. Okay? So that we're going to start at A and go across J minus 1 intervals. That takes us to the left side of the jth interval. We plug that into the R function, and that gives us the rate. That gives us the rate. Okay, so that was a review from last time. So we got like half of it, right? So we got most of the accumulation because we got all the completed intervals. But in terms of the formula, it's kind of like half the battle here. It's like half the battle. So we got that. Any questions? That's a kind of review. Any questions on that? And so again, what does this mean? What is this big symbol that's not scary? It's your friend, right? What does it mean? Just sum a bunch of these together, right? A bunch of these, one for each completed interval. So how this works is, it says, all right, let j equal 1. And when j equals 1, it calculates what r of a times delta x. And we get that when a equals 1. And then it turns around and says, okay, now j equals 2. And it does this. And then it says j equals 3. And it does this. And then it stops. It says, okay, I did it for all the j's, and now add those together. Right? Sum. Okay, so it's your friend because we don't, if we've got 50 intervals or 100 intervals, we don't want to write all those out. And so we can just write out the one generic interval and say we want to do it, add them all up from 1 to 100 or 1 to 50 or whatever it is. Okay, so now let's work on the change from the current interval. That's what we're going to work on now. So the question is, we've got a plus 3 delta x dx. How many completed intervals to reach the current interval? So obviously it's 3, but what's that in the big scheme of things? What is that 3? How many completed intervals to reach the current interval? What is 3 in this case? Okay. Just glad it wasn't the fire alarm. Okay. So what is 3 in this context? What is 3? Yeah. And what is that? What is that number of delta x's? How many of the completed intervals? Which is how many of them? All of them. 3. So 3 in this context is all of the intervals, right? It's all of the completed intervals. It's an important point, right? It's an important point to recognize. 3 isn't just some number of completed intervals. It's exactly all of them. That's really important, okay? It's all of them, okay? And so thus, for the current interval, the x value to get the rate, right, is going to be a plus the total number of completed intervals times delta x. That's what we're going to plug into R to get the rate for this current interval, right? So it's the x value at the left side of the current interval is going to be a plus the total number of completed intervals delta x. Should make perfect sense. To get to the left side of the current interval, you traverse across all the completed intervals. And so we're going to add a plus that total distance, which is the total number completed intervals times delta x. So we need to, and so this whole thing is, we're going to make a function out of that to make our life easier. That's good. That function is going to be called left of x. Left of x. That whole thing is going to be the function left of x. Okay? So we're going to have r of left of x, right? Because we a plus 3 delta x. Well, that's just a plus the total number of completed intervals delta x. So that's left of x. So r of left of x is going to be the rate we need. Okay, so we'll add to our picture here. All right, we'll add to our picture a new element which we call left x. It's the x value at the left side of the current interval. It's the x value at the left side of the current interval. So let's notice something about this function. What goes into that function? What is the independent variable into left x? What kind of thing does left x take as an independent variable? X value, right? It's just the current x value. It takes the current x value, this x down here, right? This x right here. Now, what kind of thing, what kind of quantity does it give back? What kind of quantity does it give back when you put in the current x value? Does it give a rate of change? Does it give a value of rate of change? Okay. Hundreds of students throughout the years have said that left x returns a rate. Don't fall into that trap. So this function is kind of different. Maybe you've never seen a function like this before, because what does it return? It takes an x. It takes an x and returns what kind of quantity? Another x. Kyle's all over it. It returns another x. So that's uncommon. So you might have never seen a function like that. So that's a little, we have to. So, and which x in particular? The x value at the start of the current interval, the left side of the current interval. So don't forget, left x does not spit a rate back at you. It gives you another x value, the x value at the left side. Then we're going to take left x and we're going to find what the rate is by putting it into R. See that? So it's going to give us that x value at the left side of the current interval. We're going to take that x and find what the rate is. Here, that gives us the rate. Okay, so I'll keep reminding you of that because that doesn't stick easily. Okay, left x takes an x, gives back another x. The x value at the left side of the current interval. Okay, so let's figure out. So pretty much the only thing left here is to figure out what is the total number of completed intervals. Given as x is increasing at any given value of x, how many completed intervals have we gone through? And so you had an exercise for this for your homework, right? So let's see how you did on that homework. So I've got a GC file here, maybe. I don't know how to do this. There we go. All right. So here is I've got a starting value of accumulation A, okay? And I'm showing the current value of x here with this blue bar and the x. Okay, and x is increasing through our delta x intervals, which I have set at 0.62. And the starting value of A is 0.87. And so the value of n up there is showing the current value of x. So I'll just blot that out. Do x instead here. So the current value of x is being shown up there. I'm using the n slider for that. And so we can come along here and say, pause. And so at any pause here, I'll go a little further. There we go, perfect. All right, so pause. How many completed intervals do we have for this current value of x? Can you see that there's a number of completed intervals and then x is in some current interval? So there's going to be a partial interval according to the current value of x. So the question is, how many completed intervals are there? Starting at A to the current value of x. How many are there if A is 0.87, delta x is 0.62, and we're at x equals 11.638? How many completed intervals are there? Well, we could count. Like 1, 2, 3, 4. That's not going to be very efficient when these get smaller, right? And I got a lot more of them. So if I don't want to count. So figure it out. Go. How many without counting? So this should be a review of what you did in your homework. How many completed intervals are there from A to x? How many are there from A to x? Figure it out. I'm going to call on somebody. Okay, where's Brandon Ruiz? Brandon. Make sure you come. Make sure you respond. Preston. How many? So I don't just want an answer, but what was your process of thinking about how to figure out how many completed intervals there are? What's that? But I'm trying to figure out how many completed intervals there are. That's the question. Patrick. Jacob, sorry. Jacob. Okay, let's slow down a little bit. So what does x minus a mean? So why do we start with x minus a? What is that? From where to where? Okay, so x minus a would be what? This whole like distance, right? This whole change in x from here to here. That would be x minus a. And what do we want to do with that? We're trying to figure out how many intervals there are there. So there's x minus a. Okay. And what is that? Slow down. So you want to divide by delta x. Why? What does that do? He said they'll give you how many delta x's there are. They'll give you how many delta x's there are. How does it do that? Well, so delta x is the width of each interval. So we're asking how many of those widths, right? How many of those widths fit into that total width, right? How many of those widths of delta x make up or fit into the total x minus a? And so when you do that for this calculation, what do you get? So we want to do x. Did you do that, Jacob? Just so far, what we got? Yep. 0.62. Looks like more than 10, isn't it? 17.37. Oh, sorry. Okay, so the top is 10 something. Okay. All right. So how many completed intervals are there? What is the 0.37 about? Yeah, so 17 then is our completed, right? Whole value, completed. And then the 0.37 is it dx? So what is it? It's like a percentage, right? It's like the fraction of delta x that dx is, right? So that 37 is like dx over delta x. It's the fraction of a whole interval that you have in addition to the 17 completed intervals. So if you think of 0.37 as like a 37% of an interval, or that fraction of a whole interval. But we wanted completed, so completed is 17. 17 completed. And so let's do just one more, just make sure we got it. So let's make it more interesting. And let's start at a different a value. How about 1.3? Start at 1.3. We'll have a delta x of 0.24. And we'll make there we go. That's a good one. And x is 14. Okay? So we're going to go from 1.3 to 4. The current value of x is 14. And a is 1.3. Delta x is 0.24. And so how are we going to set that up? It's going to be we got it. So same thing as before. We're going to do what? X equals 14 minus 1.3. What's the 12.7 mean? Total distance from A to X. So it's like the net change, the total change in x from a to x, and we're going to divide by delta x, and you get 52.917. Anyone else get that? All right, so how many completed intervals? Not 53. It's not. We're not rounding. We want how many whole value intervals we have. That's going to be 52, and then we have almost the 53rd, right? Like over 90%, we're into that 53rd interval, but we don't quite have it yet. Okay? So what are we doing? We're not rounding. We're not rounding. We're just chopping off the decimal. We just want to take the whole part of it. We want to take the whole part of it to get number of completed intervals. That is called, to do that the mathematical operation that does that is called the floor. So if I type in FLOOR, I get these brackets that have kind of the bottom shelf, but not the top, indicating the floor. So if I take that right there, copy it and put it in there, it does the same calculation, but then this floor does just what we need it to do. It chops off the decimal, it just gives us the whole part. So that's called the floor function. That's called the floor function. And so to get the total number of completed intervals, what are we going to do? We're going to do the floor of what? The floor of x minus a, total width of the whole interval. How many delta x go into that? And then this chops off the decimal and gives us the number of completed intervals. Which in this example was 52. So in your homework, you had to look at the number and manually chop it off, right? And say, oh, I got, what, 78.326 intervals, so I got to chop off and take 72. Well, there's this thing called the floor function is the mathematical operation that does that for you. And GC knows it, right? So GC just does it for us, right, like that. But then generally, for any value of x, and so let's try something here. I've never tried this before. What if I put n in there? And then let's make, yeah, so let's go a little slower here. What if I put n in there and then I set it in motion? Watch. Well, let's see, and let's see the one without the floor. Ready? See what's happening? So the first one is giving you exactly how many intervals it is from a to x. Second one, with the floor, is telling you the completed. So do you see how the floor works? Does it make sense? Okay, so we've got it. We've got like everything we need now for the one rule accumulation function. This was kind of the last piece to figure out how do we mathematically write the number of completed intervals. Well, it's right there. So let's go back and let's finish it. All our hard work for the last month is now going to pay off here. So now we can say, how much do we have at any current value of x? Okay, how much do we have at any current value of x? Well, it's going to be, in the big picture of it, it's going to be the total number of completed intervals, accumulation due to the completed intervals. Now, it could be more than 3. It could be 50, it could be 100, it could be 1,000. So it's going to look like this, though, right? It's going to look like this, and we know that we can write that as summation, right? Summation of all of the little changes for the completed intervals, plus the accumulation so far in the current interval. And we saw that that's r left of x times dx, right? R left of x times dx, and then now we know how to write that left x function. So let's just say, what is left x now? Left x equals, what we said? No, it's not floor. Remember, left x was start with a, and you go across how many completed intervals? All of them, which is the total number of completed intervals. So that's the floor of x minus a over delta x. So remember we said left x was, to get to left x, you're going to start at a, down here, start at a, and add the total number of completed intervals. You can sweep across all the completed intervals. And we just found out that total number of completed intervals was that, multiplied by delta x, plus a gives you that left x value. So now, we want this whole thing to be a function of x, so we don't want dx. So we want to write dx in terms of x. So we're going to look down here. How can we write dx in terms of x? Figure that out. Take a minute to figure that out. How can you write dx in terms of x? Because we want this is a as a function of x. So we don't want x and dx in there. We just want x. So figure it out. Talk to the person next to you. How do you write dx in terms of x? And you can, so right there, how can we write what dx is? Are you Blankenbaker? Yeah. You're up. Okay, Robert's up. So Robert, how do I write dx in terms of x? So this is the current value of x is here. That's where dx ends, right? That's like x final for dx. So what would it be? The starting value of x, which is what? Yeah. What do we call the starting value of x? Left x. Right. So, did you say x minus left x? Oh, did this wrong. Okay, that comes later. So yeah, so x minus left x. So that writes dx in terms of x. Right? So we got the rate in the final current interval, and then times the dx, that little portion of a full interval is going to be x minus left x. Okay, the very last thing we need to know then is when we're summing up, how many completed intervals do we have at the current value of x? How many completed intervals there are? That's how many things we need to sum together for any given x. So, how many completed intervals? How many completed intervals are there? Where's Brennan? Yeah. How many completed intervals? Given a value of x, how do we write the completed number of intervals? Right, you got it. That's what we just figured out on the GC file. It's this, number of completed intervals. So that's going to be how many things we sum together, and that'll be on the top of the sum sign. How many completed intervals we have. Okay, and we already did that. It's x minus left of x. So we have it. We've got everything. We got the whole thing in one rule. So remember, we did these accumulation functions one line, one piece at a time. We had all these different lines. And so if we had lots and lots of intervals, we'd have a line for every interval. Well, now we just have one rule that does that whole function of the whole piecewise function. So we celebrate. Okay? But that's not the end. That's just the beginning, okay? This is just the beginning. We really got to understand this, right? There are a lot of details that we had to put together to get this to work. But never lose sight of the big picture that essentially this whole thing is just what? Adding together m times change in x plus m times change in x. We do it lots of times for the completed intervals. M times change in x over and over again, plus one more m times change in x. So we're just, in essence, this thing is just summing up dy's. It's just summing up a bunch of changes in our quantity y. Each one calculated by m dx. Okay, so let's practice this with the graph. So we've got a scenario here. We're going to spend some time I don't know how to get there. I guess I got to close this. There it is. Wrong one. Where is it? This one. Okay. So I've got this scenario here. I'm unloading. I've got a truck, and there's a bunch of sand on the bed. Okay. And so then at time equals 0, the bed is going to start raising up, and this graph is showing as seconds go by on the x-axis, it's showing the rate of change of the weight of sand on the scale after it falls off the truck as a function of time. So what kind of function is this? R of W. What kind of function is this? Exact rate of change. Okay. And so why does this graph make sense? Why would the rate of change function look like this in this scenario? So you got the truck, it's going to lean back like this, and the sand is going to pour off the truck onto the scale. Why would the rate function look the way it does? Yes, sir. So is the weight increasing to a maximum, and then is the weight decreasing? Okay. Right. So the weight is going up the whole time. Does everyone see that? So why? So anyone else want to chime in? Why is this a realistic rate graph for the situation, in terms of how the sand would come off the truck? Yeah. Slowly start coming out at first. Right. Most of it comes out, and then. Right. So yeah, it's going to come out slowly at first, and then in the middle, it's going to most of it's coming out per second, and then at the end, there's going to be some left, and that will come out more slowly. Right. That the weight will be added to more slowly as we get to the end. Right. So it's in the middle. It's in that middle time frame when it's the weight is increasing the most rapidly. Most of the sand is falling off. Okay. So let's take a look at. So then, in order to same thing here. So in order to build this, so we got the exact rate function. Now I'm showing it in a different scale. To build this approximate accumulation function, where did we go from there? What was next? Approximate rate, which is our. So we had this. So this is showing what is our moment width. Can you see what our moment width is? That this is showing? 0.4 seconds is the moment width, and we're using the left side of each interval to get the constant rate for that whole interval, just like we've done before. Okay, so we're taking moments of 0.4. And so based on this approximate rate function, can you quickly sketch what you think the approximate accumulation function will look like? So you're looking at the blue steps, right? You're looking at the constant rate, constant rate, constant rate. What do you think the approximate accumulation function, can you sketch it in 30 seconds? What will that look like? So what is the accumulation now of weight, right? That's rate of change of weight. This is now accumulation of actual pounds on the scale will look like how, according to the approximate rate function. Try to sketch it. Go. So how does the weight increase at first? How does it increase at first? Right, a low constant rate. And then as some time goes by, how does it increase? Here it's increasing, weight's going up the fastest, and then as a little more time goes by, then the weight goes up more slowly again. And so you were telling me what it looks like. Right, but will it be smooth and curved like that? What will it be like? Exactly. He's drawing it perfectly with his finger. He's going like this. Like that. So let's show it. So now it's increasing the fastest rate, and then it starts increasing a little more slowly, and then increasing even more slowly again. How many people had that, at least in your head or on paper? Okay, lots of you. It should make sense, right? The weight is increasing the whole time. Why? Because the rate of change is positive. And so it increases slowly at first, then fast in the middle, and then again slowly. Okay, so we're going to look at this, and I'm going to show you some things on this graph, and we're going to figure out how it relates to our A function that we just built. So I'm going to show you some question marks here. So look on the y-axis. I want you to relate these quantities that these values that I'm showing on the y-axis as distances on the y-axis. Relate those question marks to the A function. So what do those question marks, those values, or changes in y, right? Those are changes in y. What do they represent according to the A function? Take 30 seconds or a minute to talk about that with the person next to you. What are those question marks representing? What values or changes are those question marks representing in the A function? In the A function. Go. Where's Christopher Woodard? Christopher, how'd you do on this? Did you have an idea? What's that? Okay, but there's no delta y in this equation. So in this that we just formulated, what are those values or changes of those question marks according to this in the A function? Okay, so he's saying that it has to do with this part over here. Agree or disagree? All right, volunteer. What do you think these question marks mean? Somebody new. Aiden, you haven't gone today, so Aiden, what do you think? Okay, but so I'm not just asking about the question marks. Do the question marks have to do with the right side? They're changes in y. So which changes in y are there? For each, what do we call them? Completed intervals. So this was when, what? J was 1. When j was equal to 1, it calculated an m times delta x. And that was a little change in accumulation. That's how much it calculated for j equals 1, right there. And then this one was for j equals 2. Okay, so the question mark shouldn't be j. So that's for j equals 1. What is it? It calculated m delta x. So it's called m1 delta x. m1 being what you get when you put j equals 1 into that. And then this next one is like m2 delta x. So that's j equals 2. J equals 2. Put j equals 2, you're going to get a rate. That's m2 times delta x is the change in y for that second completed interval. Do you see it? So this is for what? J equals 4. So those question marks are showing each individual change in y or each individual accumulation of sand for each completed interval. Completed interval number 1, completed interval number 2, number 3, number 4. Do you see it? Next one. Here we go. What part of the equation am I representing now? What part or parts of the equation am I representing now? Talk about it. Go. So that ordered pair would be the same as the two question marks on the axes, right? I'm just kind of repeating myself. It's the ordered pair, which is an x value and a y value. Okay, so there's really an x coordinate being represented here and a y coordinate. So that's that ordered pair, x being shown down there, y being shown there. Where's Benjamin? Leigel. What did you say? So what about the x coordinate? What would that be? What part of, or parts of this equation would that x coordinate be? What's that? Okay, well that would be what? That's the number of completed intervals. So is that the number of completed intervals? So let's start with this. Is what I'm representing here have to do with the left side, the summation, or does it have to do with the right side? Left side. What is it about the left side that I'm representing at this point? So let's say maybe the y value first. What is it about the left side that I'm representing by this y value? What's that? What value? That's the question. What value is it? What is this y value relative to this left side of this? Yeah. There's no delta y in here. There's no delta y in here. What about this is this y value? It's the whole thing. It's the sum of all the accumulation from the completed intervals, right? Because this is now the current interval. It's not including that. It's the sum of all the accumulation. This y value is the sum of all the accumulation from the completed intervals. Do you see that? That's the first question, like from before. It's the first, the second. And so what is that? That's this whole thing. It's the sum of the accumulation from the completed intervals. So that whole thing is this y value right here. Or this here. Do you see it? Before, I showed you them one at a time. I showed you them in pieces. If you add them all up, that's the summation, right? The summing all of them up. Can we do one more quick? Let's do one more. Okay, what does this have to do with the a function? This one's easier. What does this have to do with the a function? What is it referring to? What do we call it? The current interval. So is it the left or the right? It's the right. What is the x coordinate that it's showing? You got it. Say it louder. It's showing dx. It's showing dx on the x. What's it showing on the y? So the x coordinate is? It's showing dx here, the amount of change in the current interval. Here it's showing, what is that? It's the whole thing. It's the little amount of change, mdx, for that last interval. That's what that is, mdx. So we're going to add that, a little bit more of accumulation to all the accumulations in completed intervals. Okay, we'll have a written quiz Friday. Practice quiz will be up sometime this afternoon. If you have questions, come on up.
Two questions. The first one was the test next week. It's going to be in Wexford, Boston.
Same place.
Okay. And the second one was I'm not going to be able to make it on Friday because I thought it was in the evening, like at 6 o'clock.
No, it's
but I have a class at
so you can't do either one?
No, I can do Thursday.
Just, yeah, come Thursday. It's fine.
Okay.
Yeah.
So the question marks on the y-axis.
This one or the previous one?
The previous one.
Previous
the first one.
So you guys have a question about this one?
Yeah.
All right.
No, the previous one.
The previous one?
Yeah, which
Previous
one?
one.
Yeah, which one was that?
All right. So let's do that. This one. This one?
Yeah,
Okay. What's up?
I thought the left side, the y question mark, is the whole thing on the left,
No,
right?
because
No?
there's still, it's not including the partial interval. Do you see that? So if I go back a little bit here.
Okay.
See, it's not including. Wow. There we go. Stop. All right. So here, now we've got more accumulation from the current interval, which is
Okay.
not included in this, right? So I'm just going up to here.
That's the
It's easier to see if
completed
it's animated. See that it's not the whole thing because there's always the amount of the current interval that I'm not including when I do this. See that?
one. Mm-hmm.
So to here,
Yeah.
it's not all the accumulation. It's not all the accumulation. There's still more from the current interval. So what is it? It's back to the last completed interval. Right? So we just completed the first interval now. So that's the amount of accumulation from the first interval.
Okay.
Now we completed 2 intervals. That's the amount of from the 2. Now this is from the first 3. Now we got the first 4. You see there's more accumulation from the current interval. Do you see it?
Yeah.
Are you better now? What about you guys?
We were just wondering the x coordinate. So we said what the y is.
So what do you think? One way to say would be left x.
You would be using it to find your change and not use the x.
Right, it's left x. So you could say left x, or you could say a plus that completed intervals times delta x.
Oh, that's the
The
x.
thing about left x is it is left x, but left x we're using for the current interval.
Okay.
So it doesn't really. Yes, it is exactly left x.
Okay.
But normally we're using left x in the current interval situation, but here, yeah, it is left x. But it's a plus delta x times the number of completed intervals. You guys good?
Can you go back to the other one?
Which, the last one?
Yeah.
The red one?
Yeah.
Okay.
You said that this side, the
Vertical,
was
uh-huh.
the dx. Is that what you,
No.
on the x coordinate? My bad.
So what dx is the amount of change in the current interval, right? So it's the
Right.
amount of change of x in the current interval.
Right.
And then for that change in x, we get a change in y,
So
according
this
to that
thing-
rate. So
So
it's,
this thing's a change in y, right?
yeah, uh-huh.
Okay.
And
right.
that's the whole thing. That's that whole right term,
Yeah, the right side, right?
m times dx,
Yeah.
because that's m times dx.
Right.
Uh-huh.
All right, I got you.
Cool.
Thank you, sir.
I just wanted to check that the floor function is that